Consider a function f of x is equal to 2x minus 1, where x belongs to the open interval -2, 2. The ordered pairs satisfying the function f of x are -1, -3, 0, -1, and 1, 1. With these ordered pairs, the graph of the function can be obtained, which is as shown. Let's now jot down all the observations that we get from this graph. Since there are no gaps or breaks in the graph, the function f of x is continuous on the given interval. The derivative of f is equal to 2, which is greater than 0. Therefore, f is strictly increasing on the open interval -2 to 2. The given interval on which f is defined is an open interval. This means f is not defined at the end points of the interval. Therefore, f has neither a maximum value nor a minimum value. Also, there are no turning points in the graph. So f has neither a local maximum value nor a local minimum value. Let us now see if there is any alteration in the observation. If we extend the interval from open interval -2, 2 to closed interval -2, 2. Now, the ordered pairs satisfying the function f of x are as shown. If you observe the graph in this case, it is defined at the endpoints too. So, the continuity and the differentiability of the function remain unaffected. However, it certainly does have a maximum and a minimum value. The minimum value of the function f is -5, and it is attained at x is equal to -2. And the maximum value of f is 3, which is attained at x is equal to 2. However, function f still doesn't have local maximum and minimum values, as there are still no turning points in the curve. The maximum value 3 of f at x is equal to 2 is also called the absolute maximum value, or the global maximum, or the greatest value of f on the closed interval -2, 2. Similarly, the minimum value -5 of f at x is equal to -2 is called the absolute minimum value, or the global minimum, or the least value of f on the closed interval -2, 2. Let us learn to find the absolute maximum and minimum values of a function on a closed interval. Consider the graph of a continuous function defined on a closed interval x1, x8. Observe that the function has local minima at the points x2, x4, and x6, and the corresponding minimum values are the values of the function at these points. Also, local maxima occur at the points x3, x5, and x7, and the corresponding maximum values are the values of the function at these points. The absolute minimum value of the given function is the minimum of all the values of the function at these critical points as well as at the endpoints. Also, the absolute maximum value is the maximum of all the values of the function at these critical points as well as at the end points. Mathematically, a function f defined on a closed interval I is said to have absolute minimum value at a point C in I if f of c is less than or equal to the value of f at any other point on I. The number f of c is called the absolute minimum value of f on I. Similarly, a function f defined on a closed interval I is said to have absolute maximum value at a point C in I if f of c is greater than or equal to the value of f at any other point on I. The number f of c is called absolute maximum value of f on I. Let us now learn some important results that will help us find the absolute minimum and absolute maximum values of a given function. Let f be a continuous function defined on a closed interval. Then, f attains the absolute maximum value and the absolute minimum value at least once in that interval. Let f be a differentiable function on a closed interval. Function f is said to attain absolute maximum value or absolute minimum value at a point alpha in that closed interval if the derivative of f at alpha is equal to 0. Local maxima and local minima of a function occur alternately, which means that between every two local maxima there is one local minima and vice versa. Local minima at some points may be greater than local maxima at some other points. Let us now apply what we have learned so far to find the absolute minimum and maximum values of a function f on the closed interval -1, 2. To find the required values of the function f, we have to first find its critical points, which are obtained by equating the derivative of the function to 0. This gives 4x into 3x minus 4 is equal to 0. This implies that x is equal to 0 and x is equal to 4 upon 3 are the two critical points. Next, we find the value of the function at these points. The value of the function f at x is equal to 0 is 1. The value of the function f at x is equal to 4 upon 3 is minus 101 divided by 27. Also, we find the value of the function at the endpoints of the interval. We get f of -1 is equal to -11 and f of 2 is equal to 1. The absolute maximum value is the maximum of all the values of the function at these critical points as well as at the endpoints. Thus we conclude that the absolute maximum value of f on the closed interval -1, 2 is 1, occurring at x is equal to 0 and x is equal to 2. Also, the absolute minimum value is the minimum of all the values of the function at these critical points as well as at the endpoints. Thus, the absolute minimum value is -11 which occurs at x is equal to -1. Hence, the absolute maximum and minimum values of the given function on the given interval are 1 and -11 respectively. Let us now learn the working rule to find the absolute maximum and absolute minimum values of a function f on a closed interval a, b. First, find the derivative of the given function. Then, find all the critical points of the function by solving the equation obtained by equating the derivative of the function to 0. After that, find the value of the function at all the critical points and also the value of the function at the end points. Now, the absolute minimum value of the function is the minimum of all the values of the function at all critical points as well as at the end points. Similarly, the absolute maximum value of the function is the maximum of all the values of the function at all critical points as well as at the end points.